So, encoders, they are used for one purpose, which is for which you can say it is a reverse of this decoder functionality. So, it is a combinational logic circuit that essentially performs the reverse of the decoding function, and an encoder, it will accept active level on one of its inputs representing the digit such as a decimal or octal digit, and convert it into a coded output such as a BCD or binary. So, what we mean is something like this. So, it is a box. Okay. So, if this is the logic circuit for the encoder, so it will be accepting a number of lines as inputs. So, these are inputs, and at any point of time only one of the inputs will be active. So, others would be in deactive. So, it does not allow by definition more than one input to be high simultaneously. So, it will allow. So, it is expected that whoever is operating this encoder circuitry will make only one of the inputs active at a time, and accordingly you have got this output. So, this output will tell the number of the number of the input which has been made active. What I mean is, suppose this side I have got say 8 inputs. So, I have got say 8 inputs, and then say input number so these are the input numbers. So, 0, 1, 2, 3 etcetera. Now, suppose this input number 3 has been made active. So, this is equal to 1 and rest are all zeros as far as the value is concerned. So, this is made equal to 1 and rest are all equal to 0. Then on the output side, what will happen? So, this will output the bit pattern 0, 1, 1, telling that the third input had been the input 3 has been made high. So, this is the so this is actually encoding the number, the input number which is active now. Okay. So, that is how it is the encoder. So, instead of telling the number directly, so you can send a 3-bit pattern, like if you want to tell at this point of time which input is high. So, if you do not have this encoder circuitry, then you have to give this 8-bit pattern, and in that 8-bit pattern whichever input is 1. So, that will tell us that that input is active. So, that will require 8-bit of information to be communicated. However, if you use this encoder circuitry, so you can transmit a 3-bit information. Okay. So, that has got the number directly. So, that is the purpose of the encoder. So, encoders can also be devised to encode various symbols and alphabetic characters. As I was telling, the process of converting familiar symbols or numbers to a coded format is known as encoding. So, encoder performs encoding operation. So, most of the decoders accept an input code and produce a high or low at one and only one output line. So, why is it told that encoder is the reverse of decoder? So, this is the thing. So, in a decoder, what happens is that if this is a decoder, so this decoder, it accepts some input, say n inputs, and then it has got 2 power n outputs. It has got 2 power n outputs, and depending upon the input combination, one of the output is made high or made active, others are made low. So, decoder, you can say it identifies, recognizes or detects a particular code. So, it can tell you which pattern you have applied here accordingly. So, from the code, so it can identify the pattern that you want to apply. Then the opposite of the decoding process is the encoding, and it is performed, the logic circuit that does it is the encoder. Encoder has a number of input lines, only one of which will be active at a given time, and produces n bit output code depending upon the which input has been activated. So, we will see how to design this circuit and all. So, this is the block diagram. So, we have got this A0, A1, A2 up to A m minus 1 as input lines, and then we have got, so that is there are m input lines, out of which only one is high at a time, and then at the output side we have got O0 to O n minus 1. So, n output lines. So, that will be identifying which of these m inputs is high. Okay. So, that is the encoder functionality. Now, how do you realize the encoder? By means of basic logic gates. Okay, so, this is an octal to binary encoder. So, it has got one octal input, okay, and then it is say if the octal inputs A0 bar say A0 A1 up to A7. So, whichever value you want to output, so 0 or 3 or 4 or 5 or 7, accordingly the corresponding input line will be made equal to 0. So, for 5, for example, the A5 line will be made equal to 0 and all other lines will be made equal to 1. So, this output will be coming in terms of it will identify which input has been made active. So, accordingly it will be outputting the bit pattern. So, if the fifth input has been chosen here, see if I as an input. So, if I given A5 equal to 0 and rest are all 1, then it is expected that here I will get the bit pattern 101. Okay. So, how does it happen? So, if all of them are 1 and this A5 is 0, you see that all these bits are, so wherever this A5 is going, so this line is 0, we are getting a 0 here and here it is getting a 0, and on all other places, so I have got a 1. At all other places I have got 1 in this circuit. So, what will happen? So, it is inverted and then OR. So, this is basically the NAND gate, and NAND gate all inputs being equal to 1, output is 0, and if any of the inputs is equal to 0, output is equal to 1. So, you will get the pattern 101 at the output. So, this A5 being equal to 0, output is 101. If A0 is equal to 0 and rest are all equal to 1, then what happens? If A0 equal to 0, then and all other, so A0 line is not connected to anybody. So, all these inputs that we are getting are 1. So, as a result the NAND function, so this will give all 0 here, this will also this will be 0 and this will also be 0. So, the 0 0 0 will be the output, which definitely identifies the A0 input. So, this way I can design this encoder circuitry by using NAND gates, okay, by simply connecting some NAND gates. So, we can design this circuit. So, a low at any single input will produce the output binary code corresponding to that input. So, if I have a low at A3 bar, so that is A3 bar here. So, if I have got A3 bar, so it produces O2 equal to 0, O1 equal to 1 and O0 equal to 1. So, which is the code for 3. So, this way it is done. So, we have already explained how this circuit is operating. So, we can get it like this. Now, one important constraint that we have put on the operation of the encoder is that at any point of time only one of its inputs can be equal to 1. So, many a times it is difficult to ensure that in the practical operation. So, it may so happen that the inputs are coming from different sources, and as a result it is simultaneously more than one input is becoming active. But even if they are active, so we may want to give priority to some of them. What I mean is that so suppose I have got a block like this. I have got a block like this and it has got say 4 inputs. So, 4 inputs. Now, it has got 2 outputs. This is an encoder. So, if this so these are the lines 0, 1, 2, 3. So, if the line 1 is active and 0, 2, 3 are inactive, then the output should be 0, 1. That will identify. So, if I take this as the MSB, if I take the lower one as MSB, so this will be 0, 1. That will identify the input which is equal to 1. Now, if this 1 and 2 are simultaneously equal to 1, then also we may say that I will give priority to 1 and this 2 the 2 input also being equal to 1 will just be ignored as long as the input 1 is having equal to 1. So, that way this input 1 has got higher priority than input 2. So, a priority encoder is a function, is an encoder that includes the priority function. So, if two or more inputs are equal to 1 at the same time, the input having the highest priority will take precedence. So, it may be like this, that see here. So, this if all the inputs are 0, then so this truth table. So, apart from this x y, so there is another output valid. Okay. So, there is another output valid. So, you can say that it is a 4 bit input. So, you have got this D0, D1, D2, D3. So, this is D0, D1, D2, D3 plus there is. So, there are two outputs x and y, and there is another output which is valid V. So, for the operation, so we have to look into the valid bit. So, if the valid bit is not equal to 1, that means whatever output is produced as at x y, so that is not a valid combination. So, when this D0, D1, D2, D3, so they are all equal to 0. So, we say that x and y they can assume any value, but this valid bit should be equal to 0. So, that is an invalid bit. Then if it is 1 0 0 0, that is only D0 is equal to 1. So, then there is no problem. So, only one of the inputs have become equal to 1. So, we can say that output should show that the input 0 was 1. So, it is the x and y is 0 0, and this valid bit is equal to 1, telling that it is valid. Okay. The pattern outputted is valid. Now, if D1 equal to 1, then whatever be the so if D1 equal to 1, D2 equal to 0 and D3 equal to 0, then without looking into the value of D0, so it will output 0 1. So, it will so if this is the condition that D2 D3 are equal to 0, D2 D3 are equal to 0, but D1 equal to 1. So, it will not consider what is the value of D0, it will straightway output 0 1. So, that is it will tell that now input 1 is equal to 1. Similarly, if it is if the input D2 is equal to 1, then irrespective of the values that we have in D0 and D1, if D3 remains equal to 0, so then this x y should be 1 0 and the valid bit should be 1, telling that input 2 D2 is 1. And finally, if D3 is equal to 1, it does not consider whatever the values we have in D0, D1 and D2, it produces output as 1 1, telling that D3 is high. So, you see that this line D3, it has got the highest priority. So, if D3 is equal to 1, we do not look into other values of D0, D1 and D2, and we are straightway telling it the output is 3. On the other hand, if D3 remains 0 and D2 equal to 1, we are do not considering D1 and D0. D3, D2 both being equal to 0 and D1 equal to 1, we are not considering D0. And we are considering D0 only when these D1, D2, D3 all of them are equal to 0. So, I can say that D3 has the highest priority, followed by D2, followed by D1, followed by D0 for getting identified at the output. So, this is the function of this priority encoder. So, as if we have got 4 inputs and there are priorities. So, priority of D3 is the maximum, followed by D2, followed by D1, followed by D0. So, we can in addition to two outputs x and y, the truth table has a third output V, which is a valid bit indicator and is set to 1 when one or more inputs are equal to 1. If all inputs are 0, there is no valid input and V is equal to 0. Now, the don't cares that we have in the output column indicate that these input columns, similarly we have got don't cares in the input column also. So, that actually makes the truth table more condensed. And the priority that we have is like this: the higher the subscript number, higher the priority of the input. So, input D3 has the highest priority. So, regardless of the values of the other inputs, when this input is equal to 1, output x y is equal to 1. Is equal to 3 1 1. So, this way we can have this priority function. So, if we are looking into this design, so we have got this x, if you draw the truth table, then it will be like this. So, x equal to D2 or D3, then this y equal to D3 or D1 D2 bar. Okay. So, similarly, so from this you can so x and y you have got, and this valid bit is equal to 1 if all of them are not equal to 0, at least one of them is equal to 1. So, this here there is a slight modification in the circuit. So, instead of ORing D0, D1, D2, D3 separately, so we have already done an OR of D2, D3 here for getting the value of x. So, that has been utilized here for getting the value of V. So, in this way we can design a very simple logic circuit for realizing this 4 input priority encoder. Next, we look into another fundamental circuit element which is known as multiplexer. So, multiplexers, so they are also called a data selector. So, it is like this, that a multiplexer, it is a device that allows digital information from several sources to be routed onto a single line for transmission or over that line to a common destination. So, multiplexing is very common, like in say when we are, let us say, telephone line, it is carrying signals from several people and it is multiplexing between the people pair that are talking. So, that way, so there is a multiplexer. So, it is actually sometimes it is selecting one data item, some other time it is selecting some other data item to be transmitted through the channel. So, the basic multiplexers has several data input lines and a single output line, and it also has data select inputs which permit digital data on any of its inputs to be switched to the output line. So, a basic multiplexer is block diagram wise. So, you can say that it will look something like this, that we have got this as multiplexer, okay, and then we have got some data lines. So, it has got two types of lines. Some of the lines are called data lines and some of the lines are called select lines. So, these are called select lines. Now, depending upon the values of this and the output, this is the output and output is only 1 bit. So, we have got data lines, so which can be many, we have got select lines which can also be many, and then depending upon the values that we have put into the select lines, one of these inputs will be selected and that will go to the output. For example, if I have got say 4 data lines and 2 select lines like this, 4 data lines and 2 select lines, then depending upon the value. So, suppose it may say that if the value is 0 0, then this output will be routed to the, this input will be routed to the output. So, this corresponds to the select lines 0 0. Similarly, if the value is equal to 0 1, then this input will be routed to the output. So, this is corresponding to the pattern 0 1, this is for 1 0 and this is for 1 1. So, depending upon the input the select line combination that I have, so one of these inputs that will be routed to the output. So, this is very useful in many circuit design problem. You will see that these multiplexers, they make it very simple for realizing functions, and that will be used in designing many systems. So, a modern stereo system, a typical example. So, it may have a switch that selects music from one of 4 sources. Anyway, maybe it has got a cassette tape, CD, radio tuner, or an auxiliary input from VCR, DVD, or maybe some other sources also. Then switch selects one of the electronic signals from one of these from one of these 4 sources and sends to the power amplifier and speakers. So, that is nothing but some sort of multiplexer. So, a multiplexer does what it does is that it selects one of several input signals and passes it on to the output. So, that is the basic function of multiplexer. So, this is the select line. So, select inputs are applied here. So, depending upon the select input, as if logically we can say that this switch changes its position to from between these points, and accordingly one of the data inputs will get selected to be sent to the output. So, select input code. So, select input code. So, this will determine which input is transmitted to the output. So, we start with a two input multiplexer. So, two input multiplexer is how to realize. So, it two input multiplexer means, so when I say two input, so this 2 is corresponding to the data inputs. Okay. So, two input, it immediately tells that number of select lines that I will have is only 1. So, it is like this. So, if it is an n input multiplexer, then it has got n input lines. So, number of select lines that I should have here is log of n. So, this is n input. So, at the here I should have log of n number of select lines. So, that will be an output here. So, because otherwise I cannot select all the n inputs by applying the input to the select lines. So, we cannot apply select all. Internally, how will it look like is something like this. So, this is when say s is equal to 0, when s equal to 0, then you see that this AND gate output is 0. So, whatever be the value of I1, so you will get a 0 at this point. On the other hand, when s equal to 0, so here this input is 1. So, as a result, whatever is coming at I0, so that will be outputted here. So, this point I am getting a 0, this point I am getting I0, and this is OR of these two. So, here I will get I0. So, when s equal to 0, I am getting I0, and when s equal to 1, then what happens? So, here I will get I1, 1 will come here. So, this input is 0. So, as a result, I will get a 0 at this point. So, they will be ORed and I will be getting I1. So, when s equal to 0, then this I0 is transferred from the input at I0 is transferred to this output Z, and when I0 s equal to 1, then input I1 is transferred to output Z. So, I can say that the functionality that I am realizing is Z equal to I0 s bar plus I1 s. Okay. So, this is the basic multiplexer functionality. So, these multiplexers are often represented by this type of notation. There are several notations for multiplexer. So, this is the most common one. So, we have got these data inputs and this is the select input. So, it is written a 0 is written here and a 1 is written here, meaning that if the input if the control signal is the select input is 0, then this input will be selected to go to the output, and if this select input is 1, then this input will be selected to go to the output. So, this is a 2-to-1 multiplexer or 2:1 multiplexer. There are several names, okay, or 2:1 multiplexer. Now, if it is a 4:1 multiplexer, then the corresponding symbol is something like this. Okay, so, it will have 4 lines, 4 data input lines and 2 select input lines and 1 output. Okay. So, it will have 1 output, and again the same thing. So, if it is 0 0, then this input is selected. So, we write a 0 0 here. If select lines are 0 1, then this input is selected. If it is 1 0, then this input is selected, and if it is 1 1, this input is selected. So, this way we represent 4 input multiplexers in this form. Okay. So, we will see them in detail. So, this is the 4 input multiplexer. So, you see that when S0 and S1 these values are 0 0, then what I want that I0 should get transferred to Z. So, we can quickly check that it is happening, like when S0 S1 both are 0, then this input is equal. So, when both are equal to 0, then this input is equal to 1 and this input is also equal to 1. So, whatever we are getting at I0 is transferred to this point, whereas for this second AND gate, so this input is 1, but this input is 0. As a result, whatever be the value of I1, you are getting a 0 at this point. In this way, you can find that for all the cases, so you are getting a 0 here. So, this OR gate, so one input is I0 and rest are all 0. So, at Z I am getting equal to I0. Okay. at Z I am getting equal to I 0. So, other combinations also you can check. So, this is the functionality of a 4 input multiplexer or 4 to 1 multiplexer, whatever you call it. So, this is logic symbol for one of 4 data selector or multiplexer. So, it is also represented like this. So, we have shown you another representation where it is a trapezium like structure. So, you can also represent it by means of a rectangular symbol like this. Okay. So, normally the data inputs are marked as D0, D1, D2, D3, or we write down the corresponding decimal values that corresponding to the weight, and in the select inputs are normally written as S0, S1, and there also we tell which one is LSB and which one is MSB by putting that 0 and 1, this numbering actually. So, this S0 is so logic symbol for a 4:1 one of 4 data selector or 4:1 multiplexer. So, it can be when the select inputs S0, S1. So, they are if they are going to be low, if both are low. So, this if both are low, then this C0 will be selected. In fact, I think there is a actually this timing diagram explains it better. So, this D0, D1, D2, D3, suppose the values are going like this. Now, the select line when it is both the inputs are 0, 0, then this D0 line is selected at the output. When this S1, S0 is having 0, 1, then this D1 line is selected for. So, for this much time D1 is put at the output. After that S0, S1, S0 has become 1, 0, and when it is 1, 0. So, D2 output will be put at the D2 input will be put at the output. So, it is done here. Then it is 1, 1. So, D3 input will be put. So, it has come here. After that S0, S1 again has become 0, 0. So, in that case again D0 will be copied to the output. Then it is 0, 1. So, we will get say this D1 copied to the output. So, this way it goes. Okay. So, by looking, so if a varying bit varying signal is applied to this input symbols, inputs D0, D1, D2, D3, and this S0, S1 select lines. So, they also are having some varying time varying signal, then you can draw the corresponding timing diagram like this. So, the binary state of the data select inputs during each interval determines which data input is selected. So, this S0, S1 values, it will determine which input is selected. Here the data in this particular example, so they are going by a repetitive sequence. So, 0, 0, 0, 1, 1, 0, 1, 1, that is it is first selecting D0, then D1, then D2, then D3, again it is selecting D0, D1, D2, D3, etc. So, it is going in the sequence. So, as a result it produces this type of waveform. Of course, it is specific for this example. So, for 8 input multiplexer, so we can have it like this. So, there should be, so we assume that here we have got one enable line as well. So, this is the truth table that we are following. So, say when this enable line is E bar. So, when this E bar is equal to 0, then only this multiplexer is enabled, otherwise it is not. So, E bar equal to 1. So, this multiplexer is disabled. So, this Z bar, so Z is Z bar is high and Z is low. So, it is not selecting any of the input. So, it is just outputting a low here. Now, if this E bar is low, that is it is the multiplexer is active. Now, it depends on the values of S0, S1 and S2. If all of them are low, then this I0 line it will be coming to Z. As a result, I0 bar will coming to Z bar. So, this is one particular chip 74151. So, it has got 8 input, it has got 8 data inputs, 3 select input, 1 enable line, and it has got both output and its complemented version. So, Z and Z bar both are available. So, in this way internally you can think that the circuit is consisting of something like this, which produces the proper output depending upon the values of S0, S1, S2 and the enable line E.